All right, go and take your homework out. If you would, please, books open at page 203. Kendall, we're missing you again today. Looking forward to hopefully having you back tomorrow, and certainly praising the Lord for the improved health of your brother. Page 203, question number 10 says, in what two ways may the rotational inertia of an object be increased? Michael.
The rotational inertia of an object may be increased by increasing and distributing mass.
Okay, increasing mass makes sense. Distributing mass, what does that mean?
It was in the book and I couldn't find a second way.
You didn't quite understand what distributing the mass meant?
No, not really.
Audrey, did you come up with something slightly different, maybe?
Like distributing mass equally with substances.
Distributing the mass further from the center is what they would have wanted there. How about number 11? What is the rotational inertia of a single particle revolving about a center? And what is the rotational inertia of a whole body composed of individual revolving particles? Audrey?
The rotational inertia of a single particle revolving around the center is proportional to the particle's mass and the square of the particle's distance from the center.
That's true. So if we made an equation out of those two facts, we might get what little equation? What did you say for the second part?
The rotational inertia of the whole body composed of individual revolving particles is the moment of inertia.
That is what we call it, the moment of inertia for the object. It's the sum of all the particles, moments of inertia or rotational inertia. Number 12, what are the two other names for rotational inertia, Michael?
The two other names for rotational inertia is moment of inertia and or inertial moment.
Good. Number 13, what is the radius of a force and how is it symbolized? Audrey?
The radius of a force is a vector directed from the center of rotation to the point where the force is applied with a magnitude equal to the distance between the points. And it's symbolized as torque.
Well, it's symbolized as r. The radius of the force is just r. Torque is the product, actually, of force and radius. For instance, number 14, under what conditions does tau, that's the Greek letter T, tau, equal Fr? When is torque equal to force times radius, Michael?
Tau equals force times radius in the condition that it can't be converted to joules.
I mean, that's true that it can't. Audrey, what did you have for number 14?
It equals that whenever a force and its radius are perpendicular and the effect of the applied force is rotation.
That's the key. Good. When force and radius are perpendicular to each other. And number 15, what are the units for torque and what is the law of torque? Well, Michael, you addressed the units a moment ago. Answer the first part. What are the units for torque?
Newtons per meter times meter.
Newton times meters, or US would be
Feet per second. Feet times second.
pound feet, right? Pound feet. And what is the law of torque, Audrey?
It states that for a body given rotational inertia, changes in torque bring proportional changes in angular acceleration.
Good. So in equation form, Michael?
Tau equals I alpha.
Good. You gave a great explanation in words. Tau equals I alpha would be the equation form. But that is true, right? The torque is going to be equals, or changes in torque will produce changes in acceleration proportional to the rotational inertia of the object. All right, so let's talk about what you read about. Let's talk about rotational inertia. Next thing in your notes. Rotational inertia. Now, we know what inertia is, right? Rotational inertia. Michael, what is inertia?
An object's ability to maintain its momentum without presence of outside force.
Or to maintain its present velocity, maintain its present motion. The tendency of an object to resist change in motion, right? An object in motion stays in motion, an object at rest stays at rest, unless acted upon by an outside force, right? So, and we said, by the way, that the greater mass an object has, the more inertia it has. In fact, we defined mass as the amount of inertia present. Michael, walking at the same speed as Audrey down the hallway, would take a greater amount of outside force to stop. I can stop her easily, be a little harder to stop him. More mass, because he has more inertia, right? And then there's Kendall. We love Kendall. All right. Less inertia. All right. So that's inertia, right? The resistance to change in motion. Rotational inertia, resistance to change in rotary motion. And there's your definition. A body's resistance to change in its rotary motion. A body's resistance to change in its rotary motion. So if an object is spinning, it tends to keep on spinning. If an object ain't spinning, it tends to not spin. Unless some outside, and I'll say this for now, force, we'll clarify later, unless some outside force acts upon it, the object tends to stay not spinning or tends to keep on spinning. Now, of course, we know there are outside forces, right? We've all seen the ceiling fan. We turn it off because we got to clean it. And you wait. And you wait. And eventually you're like, I wonder if it would actually hurt my hand if I put it up there. So you put your hand up there and find out it doesn't hurt that bad after all. Unless it was going really, really fast still. But not too bad, right? And so you finally stop it. But when you do, the reason you were going to clean it, remember? And then dust everywhere because you stopped it too suddenly. But anyway, we've all been there, right? Well, eventually it stops. Why? Well, there's friction about the hub of the motor. There's air resistance, of course. That's the purpose of the fan, is to move air. So, of course, it's going to encounter air resistance because of the angled blades. But eventually it stops. But it resists that stopping, doesn't it? It tends to maintain that, overcoming those outside forces until eventually they're sufficient to stop its motion. Similarly, oh, it's hot in here. Turn on the ceiling fan. Slowly it gets up to speed, it feels like. And then, of course, it finally blows some nice cool air in the summertime, and that's happy. Especially if the air conditioning ever goes out and the ceiling fan's all you got. You know what I'm talking about, Michael?
Yes.
For how many weeks was it?
A couple.
In the summer, right?
Mm-hmm. And then we lost our water during COVID.
It's a bad day, bad days, or bad weeks, I guess I should say. So you know what I'm talking about. Up north, Zechariah was talking earlier because he moved down here from Pennsylvania. He's like, we didn't even have an air conditioner in my house up there. For a few weeks of the summer, it was bad. A few weeks of the summer. Down here, much different story. Here, I mean, you can't survive too well without heat. But I mean, you could make do without heat most days. I mean, the really cold days, but no air. You got to have the air conditioning. Up there, it's the opposite. Got to have the central heat. If you have air conditioning, it's optional. Apparently, my wife didn't have air conditioning. She was in Michigan for her first 7 years of her life. They had no air conditioning, and then they moved to Tennessee, air conditioning. Anyway, so off that. Rotational inertia. Two things affect rotational inertia. Regular inertia is only affected by mass, right? Michael has more inertia than Audrey, and way more than Kendall, because he has more mass. He's a bigger guy. Okay? He's not huge, by the way, for the record. You get to see Michael a little bit. He's not fat. These are not fat jokes, in case you're being offended for him. Okay? He's a little taller than me, and a little more built than I am. Okay? Anyway, people getting offended on YouTube. How dare he say that about his students? Anyway, rotational inertia depends on more than just mass. It will depend on mass, if you'll jot that in your notes. Obviously, a big, heavy wheel is going to be harder to start spinning than a little bitty wheel, right? You ever play with a little top? It'll spin it. Let's see how long you keep it spinning. Okay, those are really easy to spin. Okay, a great big wheel is going to be harder to spin. Similarly, the little top is spinning, like, okay, I'm done playing with this thing. Stop it. The wheel spinning, you're like, okay, I'm done with this thing. It doesn't stop so easily, right? So mass makes a difference, but also the distribution of the mass. So rotational inertia depends on two things. First of all, it depends on mass and what we call the distribution of the mass. You can think of this as how far the mass is concentrated from the center. How far the mass is concentrated from the center. We're going to take a look at both of these things here. I'm going to ask Michael if he would come up here in just a moment and help me with this. But I have two weapons of math instruction here. I have a towel bar. Okay, the thing you hang your towel on to dry out after you shower or something. Very, very lightweight. It's hollow. I don't know if you're on video, you can hear it. No problem at all for me to spin this thing back and forth. This is this I think is aluminum, if I'm not mistaken, painted with a satin nickel finish that is starting to scrape off from being in my my storage cabinet back there. This is a solid brass down rod for a ceiling fan. So this is not actually intended for cracking skulls. It's intended for keeping the down rod in the holder, and then of course it comes down and attaches the ceiling fan down here. And so it's considerably got more mass, and I can turn it, but it is considerably more challenging to spin it in my hand. They're about the same length. Very different masses. You got a little bit of plastic at the top. That is not where the mass of this thing is coming from. It's the brass down rod. It's thicker, it's brass, and so this thing doesn't really affect stuff. The mass is pretty evenly distributed in the down rod. Mass is evenly distributed here, but the actual masses are different. Michael, if you would come on up and start with the light easy one.
Yes.
Yes, we confirm that it is indeed easy, and then would you confirm that that is considerably more challenging?
Yes.
Yes, you can feel the difference, okay? Audrey is a child. She can't come up here. And so, Audrey, you stand so you don't hit your desk. But we'll have her do this off to the side. So you feel the heavy one first. Okay, so we feel that. Okay, now for the lighter one. And you can see considerably easier, right? And again, it's just a difference in the mass and the effect that the mass has. Another thing that affects the rotational inertia is the distribution of the mass. Now, I said that this bar right now, its mass is distributed evenly, right? So what I'm going to do is I've got a couple of 200-gram weights. Okay, so let's see, it's about a fifth of a kilogram. So about a little less than half a pound. Little weights here. And I'm going to tape these weights to the ends of the bar. So we'll go with the lighter bar, and we will just tape this here. Hopefully, then, the thought being that the weights will not go flying off and destroy people or property. That is the objective. All right. Using this not shiny duct tape, Kendall, because nobody gave me shiny duct tape for Christmas. And so my shiny duct tape stash is very low. If you're watching this with your dad, you might mention to him that I still don't have more shiny duct tape here. This feels like thin duct tape too. I might put a second layer on here. we don't need destruction of property. Or me. Or Audrey. Or Michael. Just kidding. I really do love Michael, I promise. He's just fun to pick on. This is pathetic duct tape. I bet this was made after COVID. She went to bed. This is really bad duct tape. Made in China. Made in the USA? What is this?
It was by the northern states.
It was by what?
Northern.
Oh, the northern states did it. Okay, the South makes good duct tape. Okay, so anyway, pretty much evenly, from the ends here, but there's a certain feel to the bar here. Let me just test that out, kind of back and forth, get a feel for how challenging that is or isn't. Okay, feel for how challenging this is or isn't, without hitting anything. Okay, we got a kind of the feel for that. Okay, now try to keep that thought in mind. I wish I had a second towel bar of equal dimensions, but we actually have it in our bathroom. So this is a spare that we had that, let me just cut that off. What?
Twist.
I'll cut it. It's easy enough to cut. I thought it was easy enough to cut.
It's stronger than you realized.
Okay. All right. So, hey, well, I put enough layers on there by now. Okay. I'm going to take the same two masses. So the bar will be of the same mass it was a moment ago. I'm just going to move the masses closer to where your hand is. So moving the radius in a little bit, or the masses in, diminishing the radius. We would say we're decreasing the distribution of the mass. And that should then decrease the rotational inertia. So let's see. Let's see if we can feel a difference, or like, no, it actually feels about the same. So, I'm just going to want a lot of this. This is so thin. Oh my goodness. I've been using duct tape for years. This is by far the thinnest stuff I think I've ever used. It is made in America, so I can't grouse about overseas productions. At least not about duct tape. Find something else to grouse about. So the question is going to be, by the time I finally get these duct taped together, will you be able to still remember what it felt like a minute ago? All right? So you can tell I'm able to do it much, much easier. Michael? You would confirm that. I mean, even though it was a minute ago when you last did it, considerably easier. Yeah, I mean, a second ago, no matter how I tried, there was no way I was going to make a sound you could hear coming whistling through the ends of this thing. By moving the masses in more, again, same amount of mass, same mass is there, pretty much the same amount of duct tape even, but by distributing the mass in closer, there's less resistance to rotation. Another demonstration we could do here, and let me lower the camera here and aim it at the desk a little bit. See if we can get that in good view here. I've got, similar to a couple of rods that are of equal size, I've got a couple of rulers that are of equal size. So I don't have two rods that match, but I have two rulers that match. And they both have a, let's see, what does this say, 20 grams? Yeah, they both have a 20-gram mass. One is taped here. Obviously, they're going to swing around the ruler. And even just swinging it like this, you can tell there's a big difference in the way that they're spinning. This 20 grams is much closer to the pivot point, and this down here is much further from the pivot point. So what I'm going to do here is try to hold this here. And I'll tell you what, Michael, if you'll come up here actually and help me with this. I'm going to hold it here, if you would, because you have that extra set of hands you can do this for. If you'll hold them so they're evenly spaced, so they're kind of spaced out level, and hold them up just almost vertical, not quite vertical. There we go. And just let them fall. All right, we'll see if we can do this without hitting the desk. Let's try it one more time. And Audrey, you're watching. Obviously, Michael's watching. By the way, thick, shiny duct tape. Just want to point that out. All right, go ahead. And of course, eventually they clonk into each other. Did you notice which one fell quicker?
The one closer.
The one with the mass in closer, right? It fell very quickly because there was little resistance to starting its rotation. This one almost seemed to hesitate a little bit before it started. Did you notice that?
Mm-hmm.
So the one falls quickly. The other hesitates, but did you see which one spun around further? Once this one got going, it took a little longer to get down to the bottom, but it swung way past because once it got moving, it maintained that rotation. So it resisted starting rotating, but once it got there, it maintained its rotation, where this one spun around quickly and just went back and forth very quickly, right? Very little resist. It stopped quick enough, went back the other way, and also finishes its rotation a little bit quicker. So hopefully, between the two demonstrations I was doing, you can see the difference, right? You can see how mass affects it. You can feel how mass affects it. And also you can see how the distribution of the mass affects the rotational inertia. Again, that's the resistance to either start rotating or the resistance to continue, or the resistance to stop rotating. Resistance to start or stop. And let me see if I can't... oh, that's all I need to do. Okay. All right, so knowing what we do of rotational inertia, since it depends on mass and distribution of the mass. By the way, which would you say, you could feel a dramatic effect there, right, by just shifting the masses in? Also, for an object, especially an object that's larger, its distribution could go outward in multiple directions. Imagining a circle, right? If you distribute the mass outward, it goes outward in what's a two-dimensional value, correct? So for that reason, we would say for any individual particle, the rotational inertia, which we're going to represent I, is proportional to the mass, and because it goes in two dimensions, the square of the distance from the center. We call that the radius. So we would say for any individual particle, rotational inertia for that particular particle is the product of mass and its distance from the point of rotation, this axis of rotation, squared. I equals mr squared. We'll consider the entire object, right? This entire bar, there's a whole bunch of different particles in it. Every individual particle, its individual rotational inertia is the mass of that particle times its distance from the center squared. But the entire object, then, would be the sum of all of its parts. So for any object, the rotational inertia is the sum of all the mr squares, the sum of all the particles. Well, that's kind of awkward to try to calculate, isn't it? Kind of impossible to calculate, really, until you've learned some calculus. So people who do know calculus already helped us out a little bit. Look at your textbook at page 194. And on page 194, people who do know calculus helped us out, and they came up with, for different basic shapes that we'll encounter from time to time, how it all works out for that particular object's rotational inertia. The good news is you don't have to memorize these. If it's in the book, you'll flip back to this set of figures and you'll say, which of these does this sound like the most? For instance, if you've got, I'm not going to use this book here. Let's see, do I have a hardback textbook in here? I do. Let's use this book here. It's got Bible stories, Illustrated Bible Story Library. Okay? If I were to take this book and I were to spin the book like this, which of these shapes is this pretty much like? Rectangular plate. If I were to take my roll of duct tape and I were to spin the roll of duct tape, which of these would it most resemble? The annular disc. If I were to take this down rod and I were to start spinning the down rod, which would this most resemble?
Solid bar.
The solid bar, right? So you see how everyday objects can equate to one of these basic shapes. If I were to take a quarter and flip the quarter in the air, well, that would match a solid disc, but which one? Notice on the first solid disc on the top row on page 194, that shows how the object is rolling around its axis. Whereas on the bottom, the solid disc is flipping end over its axis. So if I'm flipping a quarter, that's the solid disc on the bottom row. However, if I'm trying to roll a quarter, that's solid disc on the top row. Make sense? If I were rolling a hula hoop along the ground, ring. Obviously, if I rolled my ring along the desk, ring. I'll roll a ball.
Solid sphere.
Solid sphere. What about hitting a tether ball?
Revolving particle.
That would be more like the revolving particle, right? It's just a really big particle at the end that you don't want to get hit in the face with. So you get the idea, right? How each everyday object can equate to, in many cases, one of these. So we'll just, for now, if it's in the textbook, we'll look at one of these. We'll say, it looks like it's this one. If it's on a quiz or test, I'm not going to let you look it up in your book. So in that case, I have to tell you, here's the equation for I. Does that make sense? That just takes the load off of you. Let's look at some of these equations here and some of these problems here on how we use these. Example 13.6. And go ahead and read that if you would, Audrey.
What is the moment of inertia of a 2 kilogram ball swinging about a pole on a 1 meter rope?
By the way, I didn't mention this. It was in your homework. I did not mention this. I will use the term rotational inertia because I feel like it makes the most sense. It's the inertia of something that's going to rotate or is rotating. Moment of inertia. Does that make logical sense? Not really. I'm sure there's or inertial moment. I'm sure there's a reason people came up with that. Doesn't make a lot of sense to me. So I don't use those terms. I use rotational inertia. But if they use the term inertial moment or moment of inertia, that's talking about rotational inertia. 3 names for the same thing. College physics textbook may use those terms. So we go, I never learned about moment of inertia. Yes, you did. We just called it rotational inertia. Okay, so just in case that becomes an issue, I think use the term moment of inertia here. There's a 2 kilogram ball swinging about a pole on a 1 meter rope. What does that sound like?
Tether ball.
Tether ball, except it's a short rope, only 1 meter long, and it's a 4.5 pound ball. Okay, this is like extreme tether ball. This is a small bowling ball.
What's that
All right.
sport where you swing the ball?
The swinging the hammer throw, right? You got the ball on the end of the row. Is heave and wrench your back at the same time if you're me. Even just demonstrating the technique. Anyway, so anyway, maybe that's what this is. Maybe this is the hammer throw. I don't know. Well, it's something about a pole though, so that ain't it. Anyway, which of the pictures most would resemble a ball swinging on a rope around a pole? So for a revolving particle, what's the equation for rotational inertia? I equals mr squared, which is what we said it would be for a particle. We're just looking at a very big particle, okay? Where the mass, of course, here is the 2 kilograms, and the radius is the 1 meter. That needs to be squared. Well, you could do this in your head. 1 squared times 2. 2. Notice the units, though. Kilograms times meters squared. And they seriously want 3 sig figs for this. 2.00 kilograms times meters squared. There's our rotational inertia. Look at the next example problem. Example 13.7. Read that for us, Michael.
In the pioneer days, children would often use a stick to push along an iron hoop. If the hoop had a radius of 0.320 millimeters and a mass of 4 kilograms, what is the moment of inertia?
All right, you remember the, I think it was an AT&T commercial about the settlers, people who settle for lousy internet. And they actually had a settlers where the guy's like, well, I'd really like to get blah, 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 blah. Well, we should be content. You have your sewing, I have my stomping, boy has his hoop, she has her doll, we should be happy. Anyway, so the hoop, this was actually a sport or a game that they would play, is see how long they could keep a hoop rolling along the ground, right? And so, but unlike a hula hoop, it was made of iron, so it could actually like, smash your toe if it rolled over your foot. Because of course there has to be some element of danger or it's not fun for guys, yes. Right? Like football, okay? What makes it fun is that somebody could actually get hurt until somebody does, and then it's like, oh, cancel the game, forget this game, and then you're happy that somebody's feeling so much better. So we like the danger until something bad happens, and then women are like, you guys are stupid. Anyway, and just like risk, I guess that's all it is. So anyway, which of these pictures would resemble a hoop rolling along the ground? I would say the ring. What is the moment of inertia for, or rotational inertia for a ring? The reason here is because the mass is all concentrated at the edge. So the radius of it is full. Whereas, for instance, on the disk, notice it's a half mr squared. Because some of the mass is at the center, some of the mass is halfway out, some of the mass is at the edge. On average, the mass is halfway out. Right? So that's the reason for that. So I equals mr squared again for a ring. Or in this case, the iron hoop. What is the mass of said hoop? 4 kilograms. So about a 9-pound, almost 10-pound hoop. And the radius of the hoop, it says, is
0.32.
And here's where I pull out the calculator. All right, so we need to square the 0.32, multiply that by the mass, and what is the rotational inertia of the hoop?
0.4006.
And notice the units, kilograms times meters squared. Of course, we do want to use sig figs. They give us 3 sig figs, so we'll say 0.410 kilograms times meters squared. Notice, the hoop has a greater mass than the ball, the tether ball, right? Than extreme tether ball. But the tether ball has considerably more rotational inertia. Picture it. You've got this, again, radius 0.32, so the hoop is about this big across, okay? It weighs about 10 pounds and it's rolling towards you. Just imagine stopping that. Now imagine a 4.5-pound ball flying at your face, stopping that. Doesn't it seem logical this would seem to threaten you more than the other that's rolling along the ground? Right, so we can kind of see how the rotational inertia would work. They're kind of envisioning it. Example 13.8, read that for us if you would, Audrey.
The U.S. quarter 25 cents has a diameter of 24.3 millimeters and a mass of 5.67 grams. Find the moment of inertia for a quarter that has been flipped into the air and overhead.
Now the 25 cents is just there to make sure you understand that by quarter they're talking about a coin. That's all, okay? We're playing heads or tails. All right, heads I win, tails you lose. You know the game, right? And anyone ever tried that with a sibling? Because you're the older ones, right? So surely you've done that. All right, let's play heads or tails. Heads I win, tails you lose. Mm-hmm. Hey, it's tails, you lose. Mm-hmm. You know, wait a second. You know? Anyway, never done that. Never done. She's all like, yeah, I've definitely done that. And you're like, no.
I never had to. I used to have a double-sided quarter.
You had the double-sided quarters. Cheaters. All right. Anyway, it's like the deck of cards and all of them are a 10 of diamonds or whatever. Pick a card, any card. I'm getting a signal. 10 of diamonds. How did you do that? It's all telling me. Oh, whoops! Drop the cards and they're all over the floor. Like, oh, I see how you did that. Anyway, Michael laughs. You had one, didn't you?
No, I had marked cards.
You had marked cards, okay. Hey, well, that at least requires some intelligence, right? Because you have to remember the code that you have on the back of the card. So, anyway, bicycle playing cards, great for that. You have all the little spokes, you can figure out your own pattern. Anyway, not that I would ever mark cards. Anyway, dangerous thing if you get into it. Anyway, all right, so anyway, back to the problem at hand. We're flipping it, we're playing heads or tails, right? With a non-double-sided coin and end over end coin. What's the rotational inertia for the end-over-end coin?
I equals 1/4 mr squared.
Good, I equals a fourth mr squared. So we're going to have to divide by 4 or multiply by 1/4. I think it's easier to divide by 4, and you got the mr squared. The mass of the quarter, it says, is
5.67 grams.
Thoughts on that?
0.0567.
Ooh.
Oh wait.
Grams to kilograms. Got to move it
0, 0.
3 places. Right, so we're going to go with a 0.00567. I should have given myself more room. And then it doesn't give me the radius, it gives me the diameter, so I need to change that to radius. What's it come out to? 12.15 millimeter radius. Thoughts on the radius?
0.121.
But I'm going from millimeters to regular meters. Again, that's going from any -3, so move it 3 places.
0.0125.
Meters, okay? And remember, that value's got to be squared. So we'll square the 0.01215, multiply by that, but by the mass, 0.00567, and then divide all of that by 4, because it's taking 1/4, or times 1/4. And I'm going to scientific notation here. What is the rotational inertia of a quarter that you're flipping end over end? E-7 kilograms times meters squared. 0.000, like a whole bunch of zeros, right? It's initially what you had. Why? There's almost no resistance to start flipping a quarter, and there's almost no resistance to stopping it from flipping in the air, right? Very, very simple to do. And so rounding off to sig figs, it was 3 sig figs, so 2.09 E-7 kilograms times meters squared. Questions on that? You find the picture that it matches, plug it into the equation to find the rotational inertia. Good to go? All right, next let's talk about torque. And you've probably heard that term before, maybe on truck commercials, right? Heard the truck commercials for torque, and gets more torque, more pound foot of torque, blah, 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 because we're in the US, so we say those things. Well, torque is actually what causes rotation, not force, right? I can push on the door back there, and it doesn't move. Watch this. I'm going to turn the camera around here. Okay? So I can apply a force to this door, and I can cause it to move, or I can apply a force to the door, and it doesn't move. If I pull a force this way, the door moves very easily. If I pull on the door this way, it doesn't really move. Or if I push the door this way, it doesn't really move. Why not? Because I'm pushing right along the door straight back to the hinges. If I push the door like that, a component of my force is angled in, and then a component of the force is angled this way. And only the component of the force that's perpendicular to the door actually causes it to move. The perpendicular component of force, hopefully it's just straight force, right? Not like, let me open it like this. Well, okay, I'm pulling a little bit both ways, right? But the perpendicular force times the length of the radius is what causes the movement. For instance, if I push on the door way back here at the hinges, I can eventually get it to close. It'd be so much easier just to push it out here, right? And when you were little, you probably learned this, right? And okay, be honest. I get on to my kids all the time about this because I'm envisioning one of my kids getting their hand in the door as it slams shut. So I'm really big on telling them, stop playing with doors. Do not slam doors. You don't get to shut the door to try to keep your younger sibling out. Stop it. Okay, but eventually it's going to happen, right? You ever, one's on one side trying to get into your room because you're the older ones, right? Unless maybe you were trying to get into Jane's room or something. But trying to keep the little siblings out, right? So you're like pushing the door, or maybe they've got their foot in the door like this and you're pushing and they're pushing. Well, if they push closer to the handle and you pushed here, they're going to win, right? Whereas if you're both out here, it's probably a draw. Maybe you're a little bit stronger. If they're in there, you're going to win that battle. With our bathroom doors here, right? It's just kind of a kick plate, and both at the hand area and then at the foot area. So I try to teach my kids, when you go to open the door, and you lean on the door because you're little, just try to open the door, picturing Timmy, lean out where the handle part is. Or, hey kids, shut the door for me. Push it where the handle is. Why? A greater radius is going to give you more torque. Kind of like with the law of levers. Remember we said F sub I, R sub I equals F sub O, R sub O? Well, the FR there is actually just torque, right? So force times the radius, assuming they're perpendicular to each other, is torque. And there's your definition for torque. If you would go and get that in your notes, torque is the product of a force causing rotation, the product of a force causing rotation, and the radius of that force. The product of a force causing rotation and the radius of that force. And again, that's important to note, that's when force is perpendicular to radius. That's the only clarification. Force must be perpendicular. Or we're going to look at the perpendicular component of the force. We'll represent torque with the Greek letter tau, which you're familiar with from pre-calculus. Kendall, that's a new one for you. Tau equals FR. Now remember, force is measured, class, in newtons in the SI, radius measured in meters. Well, we've done force, newtons, times displacement, meters. We called it work, and we said work is measured in joules. Here's the key. Force this way, movement that way. They were collinear. You multiplied them, newtons times meters, and got joules. Here, the newtons are one way, and the meters are perpendicular. So you can't just put them together into joules. We're going to leave it as newton meters. Or in the US, remember we said foot-pounds are for work? We differentiate torque by saying pound-foot. So a foot-pound is work, a pound-foot is a measure of torque. And that's how the US differentiates between the two units. Okay, generally speaking, we'll use newton meters. But again, we don't get to simplify them to joules because they are not in the same line. This radius, by the way, remember we called it a lever arm for a lever? Well, picture it, you've got a pivot point, and you've got a force perpendicular to that radius. Technically, you're applying torque. That FR product on either side of the law of levers is torque. So we used to call it the lever arm. When we're looking at it from the perspective of torque, we call it the torque arm. So the radius is sometimes called, or often called, the torque arm. Similar to how we would have called it the lever arm previously. So again, the point I tried to make with the door illustration is force doesn't necessarily cause rotation. I applied force to the door didn't move, door didn't rotate, if the force is perfectly in line with the radius. So we have to change our thinking. Remember, we said an object at rest stays at rest unless acted upon by an outside force. An object that is not rotating tends to not rotate, or an object that is rotating tends to keep rotating unless acted upon by an outside torque. Does that make sense? Torque is required for rotation. So we're going to change our thinking. Just as we said that displacement gives way to angular displacement. We said velocity gives way to angular velocity. We said acceleration gives way to angular acceleration. Force is going to give way to torque in our thinking with rotary motion. But also, remember we said that if I wanted to start an object moving, I have to apply enough force to overcome the mass and produce the desired acceleration, right? So we had before F equals ma. Because in linear motion, straight line motion, all that really matters is how much mass does the object have you're trying to move. But when you're trying to spin an object, we just got done looking at, it's not just about how much mass it has, but how the mass is distributed. So mass even is going to give way, because mass isn't the only thing we're concerned with. We're concerned with mass and the distribution of the mass, rotational inertia. So F equals ma is fine for linear motion, but for rotary motion, we're going to say that torque is equal to the product of the rotational inertia and the desired angular acceleration. So we have two different equations for torque. The definition of torque, force times radius, and what we call the law of torque. It's Newton's second law of motion, rewritten for rotary motion. The law of torque, tau equals I alpha. Look, if you would, at page 196. Page 196, example 13.9. Page 196, example 13.9. Go ahead and read the problem for us, if you would. I think we're back to Michael.
What torque is 13.9?
13.9, yeah.
What torque is required to accelerate a wheel from rest to 100 revolutions in 30 seconds if the mass of a wheel is 10 kilograms? Assume that the wheel has an inner radius equal to 0.95 meters and an outer radius equal to 1 meter.
All right, so this wheel has both an inner radius and an outer radius. Kind of like, for instance, the roll of duct tape. There's some thickness to this wheel that we have to account for, as opposed to a really, really thin ring where, I mean, if you're looking, well, never mind, I won't take it off. But you like a typical ring, right? The inner radius, they're so close it doesn't make a difference. Here, there's some real thickness to this particular wheel. So, if we want to calculate the torque needed to accelerate the wheel, I need to account for the rotational inertia of the wheel. Looking back at page 194, what picture are we going with? The annular disk. And so the I is going to be calculated using the equation.
1/2 m times the product of r squared plus r squared.
All right, so we're going to square the two radii, add them, and multiply that by the mass and take half of it. Is that the equation you said? I think that's what you came out with. That's going to give me the I. We also need to find the alpha. How do I find angular acceleration?
Omega sub f minus omega sub I.
Do you realize I'm going to have to calculate the I, calculate the alpha, then multiply to get the torque? So I'm really using three equations at the same time. Let's start with the easier one, which I think is the alpha equation. All right, now it says the wheel starts from rest. So forget the omega sub I. It gets up to a rotating speed of, or an angular velocity of 100 revolutions per second. Wait a second, we don't do revolutions. So 100 revolutions is how many radians?
628.
200 pi, which would be about 628 point blah, 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 right? So we're going to do 200 pi per second. That's the angular velocity. And how much time did it take to get up to that speed? 30 seconds. So that's going to give us how many radians per second squared of angular acceleration here? 200 times pi, there's the 628, divided by 30.
20.94.
All right, put that in the memory of your calculator. 20.94 blah, blah, blah radians per second squared. That's the acceleration of this particular wheel. That's part of what's the torque is calculating the torque needed. What acceleration are we trying to produce in this wheel? The second factor, though, is what's the rotational inertia? How much resistance does this wheel have to get moving? So we're going to take half, or divide everything by 2 at the end. The mass, what was the mass of the wheel? 10 kilograms, okay? And then the first radius was 0.95. Okay, so square the 0.95, and the other radius was 1. But if you square 1, you get 1. So we're going to add 1 plus the 0.95 squared. What is the sum of the squares of the radii? All right, so that's the sum of the squares of the radii. Multiply by 10, divide by 2. Or multiply by 5. Would have been quicker. Oh well. And we get,
9.5.
comes out evenly, kilograms times meters squared. Okay, so we understand that's our units for the rotational inertia. If I take the value on my calculator, I, times the memory value, alpha, there's the torque I'm going to need. How much torque is needed to get that wheel up to that speed in that amount of time? Sig figs? 3 sig figs, so we'll say 199. And what do we measure torque in? Newton meters. Or pound foot, but in this case, Newton meters. All right, you're going to have a few problems to do for homework this evening and a few questions to answer as well. For homework, I need you to read over pages 203. I need you to read over pages 195 to 198. Read pages 195 to 198. On pages 203 to 204, that's where the questions are. Those aren't the pages you're reading. On page 203 to 204, answer questions 16, 17, and 19. 16, 17, 19, and on page 204, do problems 8 through 10. do problems 8 through 10. So 3 questions, 3 problems. We'll take a look at this again tomorrow as we review over. Have a wonderful rest of your day, and you are dismissed.